Hello everyone. The chapter that we are going to study today is aldehydes, ketones, and carboxylic acids. And amongst that, also we are going to study about ketones, carboxylic acids, and a few type of reactions. Okay. So this is about carboxylic acids, the basics of carboxylic acid. Let us see. Okay. So we are covering here carboxylic acids, the basics of carboxylic acids and ketones, carboxylic acids. So what are carboxylic acids? So if we talk about the IUPAC name of carboxylic acid, so you must have already studied this in class 10. In carboxylic acid, we have the COOH functional group, COOH functional group at the end, right? And it ends by the suffix OIC. Suffix means something that is attached at the end. So for example, if it is a 2-carbon compound and it has a carboxylic acid functional group, so we will be calling it ethanoic acid because this is an alkane, right? So ethanoic acid. Now this is methanoic acid, butanoic acid because it has 4 carbon atoms. This is pentanoic acid. Okay. So here we have 2 functional groups. That is, you have an amino group and this is a COH, that is the carboxylic acid functional group. Okay. So here the most priority is given to the carboxylic acid functional group. So the one that has the least priority, we name it first. We put it in the prefix, right? So we start the numbering from here, 1, 2, 3, 4. So what does it become? It becomes 2-aminobutanoic acid, right? Similarly here, okay. So this is the COOH group, right? That is the carboxylic acid. And this is the ketone functional group. Again, the priority is given to the carboxylic acid. So this is the first carbon atom, second, third, fourth, right? And we consider the longest chain, right? So we have methyl group on the 4th and the second carbon atom. So what do we name it? 2,4-dimethyl 3-oxopentanoic. Now oxo is used as the prefix for ketone, oxo. Okay, here this is COOH, that is the carboxylic group. We have Cl and Br. Now here we always name according to the alphabetical order. So we call it 4-bromo 2-chlorobenzoic acid, right? So numbering always starts from the functional group which is given the highest priority. So 1, 2, 3, 4. So even if you would have started from here, bromine would have got 5, but in that case, chlorine would have got a larger number. So this is the best way to number 1, 2, 3, 4, 4-bromo 2-chlorobenzoic acid, right? So the name for this is 3-isopropyl benzoic acid. So this group is known as isopropyl, right? Okay. So let us move forward. These are some of the common acids, right? Now in the exam, how they ask, in the exam, they will ask you write the IUPAC name of succinic acid or draw the structure of succinic acid, right? So it is very important for us to know these acids, right? So what is oxalic acid? It is ethane dioic acid. 2 COH groups together is known as oxalic acid. It is asked in the exam, draw the structure, write the IUPAC name, which is asked for 1 mark in the board exam. Now this is malonic acid, which is again propane 1,3 dioic acid. This is succinic acid. This is glutaric acid. This is adipic acid that has 6 carbon atoms and which is hexane 1,6 dioic acid. Di means there are 2 carboxylic groups. Okay. Next we have propane 1, 2, 3 tricarboxylic acid. Right. So these acids are very important. You should know the structure and names of these acids, right? Now we are coming to the basics of ketones. What are ketones? See, ketones are always attached in the middle. They are never present at the terminal ends. The carboxylic acid functional group is present at the terminal ends, but if you would see ketone, it is present in the middle. It is never at the end. See, ketone is never like this. This cannot be called a ketone, no, right? So ketone is always in the middle, right? Okay. So this is known as acetone, and its IUPAC name would be, can you all guess what would be the IUPAC name? So there are 3 carbon atoms, so it is prop, it is an alkane, so ane, propane. Now ketone functional group, we add one at the end, one, so it is propanone, which is commonly known as acetone. This is used as the nail polish remover in our daily life. Next is acetophenone. Now it is very important for us to know the structure of acetophenone, right? Because in the board exams, they ask us to differentiate between acetophenone and benzophenone, right? So if we do not know what is the structure of acetophenone, how will we distinguish between it, right? So this is benzophenone, this is acetophenone, right? Again, a ketone functional group is there. Here also we have a ketone functional group. Okay. Now here we follow like a different form of numbering. to understand several reactions. Okay. So you can see here we have alpha carbon, beta carbon, gamma carbon, and alpha dash, beta dash, gamma dash. So the carbon atoms which are next to the functional group, we call them the alpha carbon atoms, right? For example, this is next to the functional group. I call it alpha. The second one, I'll call it beta. The third one, I call it gamma, right? So this is how we can name the functional group. And also this is used to understand many mechanisms. Let us move forward. So as I told you that the suffix used here is on, right? So here you will start naming from, where will you start naming from? You will start numbering from the carbon atom which has the functional group. So we start from here, 1, 2, 3. So at the first carbon atom, the substituent is what? It is phenyl. So we have one phenyl propane, one on, right? So here we have propanone, here it is one phenyl propane, one on. Okay, here it is 3-methyl cyclopentanone. Okay, so one, obviously the functional group, the carbon which has the functional group should be given first number. So 1, 2, 3, 3-methyl cyclopentanone. On means ketone functional group, right? Okay, so you all can practice this. From where should we start naming it? So we start naming it from here because this is where our functional group is, right? So I start naming from here, 1, 2, 3, 4, 5, 6, 7, 8. So it becomes 5 bromo, 4 methyl, because on the fourth carbon we have methyl, 4 methyl octane, 2 on, right? So this is about the ketone functional groups. Okay, now we are going to study about the nucleophilic addition reactions. So let us see what are the nucleophilic addition reactions. So firstly, let us understand what is a nucleophile. A nucleophile is something that has a negative charge, right? Nucleophile, the word nucleo means nucleus, phile means loving, right? Something that loves nucleus. Now, nucleus has a positive charge. So something that would love the nucleus should have a negative charge, right? Okay. Now let us understand. This carbon is sp2 hybridized. It is trigonal planar. Now oxygen is electronegative. So it is slightly electronegative, and the carbon has partial positive charge. This is partial negative charge, right? Now there comes a nucleophile to attack. Now what do you think where the nucleophile will attack? Can you all guess? So negative will go to positive, right? Obviously. So nucleophile will go to the carbon atom. But carbon can form only 4 bonds, and this carbon is forming 4 bonds. So what will happen? There will be a shifting of the double bond. So let us see. So nucleophile comes and attacks the carbon atom. There is shifting of the double bond, right? So this is how the structure is formed, right? Now it is sp3 hybridized. Okay. So you can see it is sp3 hybridized, and all the bonds, they have an angle of 109.5. Okay. And it is a tetrahedral structure, right? So if I have water molecule as well, so hydrogen will come and attach to the OH minus ion, right? So this is called the nucleophilic addition product. I hope you understood. Let us understand it together. So we have carbon, which has a partial positive charge. Oxygen has partial negative charge. Nucleophile will come and attack the carbon, which has the partial positive charge, right? So nucleophile will come here, the double bond would break. So this is the intermediate structure. Now, if you do a hydrolysis means addition of water. So what will happen on hydrolysis? OH minus, like that is hydrogen would come here at near O minus, right? And it will form OH. Okay. So this is the nucleophilic addition reaction product. Okay. So aldehydes are more reactive than ketones in nucleophilic addition reaction. Why? Because all are alkyl groups. Let us consider an aldehyde and a ketone. For example, this is a ketone, right? And this is an aldehyde. Now it is said that the aldehyde is more reactive than the ketone because the alkyl groups, they try to increase the electron density on the carbon atom. They try to increase. So if they try to increase the electron density, this will become negatively charged. And nucleophile would not like to come to a negatively charged carbon atom, right? So that is the reason. So if they increase the electron density, the speed or the reactivity of the nucleophilic addition reaction will become slow because of the increased electron density on the carbon atom. If we look here, there is only one alkyl group. So obviously the electron density will increase, but it will not increase that much as compared to a ketone, right? So let us see. So here there is less hindrance also. Okay, so one thing is the inductive effect and the other thing is hindrance. You can see here, if I draw a okay, so in this slide, there is a ketone, here there is an aldehyde. So basically, there is less hindrance here for the nucleophile to come and attack. But in the case of ketone, there is more hindrance and less electron deficiency at carbon, right? Less electron deficiency means now it has more electron density because of the donating nature of the alkyl groups. So this affects the rate of the nucleophilic addition reactions. Okay. Let us see, these are a few nucleophilic addition reactions. Addition of hydrogen cyanide. So Cn minus is a nucleophile. It comes and it attacks on the carbon atom. Obviously, why? Because carbon atom has a partial positive charge. The double bond breaks and the electrons shift towards the oxygen, right? And here H plus is released. Okay. Now H plus is added because hydrolysis is done. So obviously positive will go to negative, and this is the product that we get. This is known as cyanohydrin, right? Cyanohydrin. Okay. Now cyanohydrin, if you treat it again, you do hydrolysis, we get 2-hydroxy carboxylic acid. Okay. Now there is one reaction which is called reduction. In the presence of lithium aluminium hydride, this gets reduced to amine. So we get CH2NH2, right? Okay. Now addition of sodium hydrogen sulfide. So basically NaHSO3, we can write it like this, right? ONA. So oxygen is obviously minus, and we have Na plus and SO2H. So obviously negative part will go and attack to the positive carbon atom, right? So you get ONA attacking to the positive carbon atom, and here there is a negative charge. Okay. So if there is a negative charge over here, so this bond will break, and SO2H has a positive charge that will go to the oxygen atom, right? So we get this. Okay. So here you get hydrogen sulfide addition compound, basically a reaction known as tautomerism occurs here. H comes here and sodium comes here for the stability. Okay. So due to the steric hindrance, rate of the reaction in ketones is very slow, we know that. And this is used for separation and purification of aldehydes, this method. Okay. So next, let us see addition of Grignard reagents. Okay. Now, what are Grignard reagents? We have studied this in chapter 1 in haloalkenes, haloarenes. Whenever an alkyl halide reacts with magnesium in the presence of dry ether, we get RMgX. Now, magnesium is very electropositive because it is a group 2 element. So, R would be negative. So, this carbon is partial positive. So, it will be attracting R. The oxygen becomes negative. So, let me draw it here. Okay, partial positive. This is negative. And we have RMgX. Magnesium is partial positive. This is partial negative, right? So R will come and attack on the positive, and this will go to the negative, right? The MgX part. So what am I getting? I am getting this. Okay. I am getting the R here, and the oxygen is attached to the MgX part, right? Okay. I'm getting H here, and since there is R dash here, so we are taking R dash. Now, if you hydrolyze it, this part gets converted to an alcohol. Right. So we get C, H, R, R dash, OH, right? So we get a secondary alcohol. So in case of an aldehyde, you're going to get a secondary alcohol. In case of ketones, tertiary alcohol is formed. Okay. So this is a ketone. As you can see here, there are two alkyl groups, R and R dash attached, and we have RMgX, right? So tertiary alcohol is formed over here. Okay. Okay, so now next is oxidation reactions, right? So we completed nucleophilic addition reaction. Now in exam, how it is asked? It is basically you are given 3 to 4 compounds, and they ask you which one of the following would undergo nucleophilic addition reaction faster, or arranged in the increasing order of the nucleophilic addition reactions, right? So I hope you can arrange it based on checking whether it is a ketone or an aldehyde. You need to look for the steric effects. You need to look for the inductive effects, right? You need to look if there is a benzene ring present, right? Okay. Now, what is oxidation? You know that oxidation is gain of electrons or loss of hydrogen, right? So now some these compounds, they undergo oxidation with agents like HNO3, KMNO4, that is potassium permanganate, and potassium dichromate. So aldehyde is there, which is getting oxidized, right? Okay, so can you see here, we have R, C double bond OH, which is getting oxidized to carboxylic acid. So ketones are, generally oxidized under vigorous, that is very strong conditions, right? So you can see here, there is a ketone, right? So ketone is oxidized under very vigorous conditions. You can see here, it is getting converted to carboxylic acid. Okay, there is a Popov's rule. What does it say? That according to this rule, which carbonyl carbon of the unsymmetric ketone, it remains with the smaller alkyl group preferentially, right? So the carbonyl carbon of the unsymmetrical ketone, right? It remains with the smaller alkyl groups. Okay. Okay. So let us move forward. So you can see here the bond breaking is happening from here, right? The bond breaking is happening from here. And the carbonyl carbon remains with the smaller alkyl group, that is the Popov's rule, according to this rule, the carbonyl group of the unsymmetrical ketone, this is the carbonyl group, it remains with the smaller alkyl group, right? It remains with the smaller alkyl group and it forms this, right? And this also, yes, CH3CH2 is there, which is getting converted to carboxylic acid. Okay. Now let us move forward. So now there are oxidizing agents like Tollens reagent, which gives us silver mirror test. So how is Tollens reagent prepared? So we take silver nitrate and ammonium hydroxide. So we get silver oxide, ammonium nitrate, and water. Again, that silver oxide, if we add ammonium hydroxide, this is the Tollens reagent. Okay, so we always prepare it very in a fresh condition. So in an aldehyde, if we add Tollens reagent, the aldehyde is oxidized. Can you see it is oxidized to RCOO minus, right? And it gives a silver mirror. So this is also a distinguishing test. Suppose if you are given an aldehyde and a ketone, so you can distinguish it by the Tollens test. Okay, can you see here in the image, you can see a silver mirror is produced, right? Okay. Now both aliphatic and aromatic aldehydes give this Tollens test. So all of the aldehydes give Tollens test. Okay, now Fehling solution. What is Fehling solution? It is a mixture of Fehling's A and B, again, which is used for oxidation. So Fehling's A is copper sulfate. This is asked in the exam. What is Fehling's A? Fehling's A is copper sulfate. Fehling's B is alkaline solution of sodium potassium tartarate, which is also known as Rochelle salt. Okay. So we mix Fehling's A and B sulfates together to get Fehling solution. Now this Fehling solution also oxidizes aldehyde and it gives a red-brown PPT, but it only oxidizes the aliphatic aldehyde and not the aromatic ones. Okay, so you can see here there is a deep blue complex is called the Fehling solution, which is formed by mixing of sodium potassium tartarate and copper sulfate. So this is aldehyde. So free copper ion is released. Right? So it gets oxidized to RCO minus and the product is a red-brown PPT, which is again a distinguishing test, but it is only given by aliphatic aldehydes and aromatic aldehydes do not respond to this test. So I hope you understood about the oxidation reactions. So let us just recall what we covered in today's video. So we saw the basics of carboxylic acids, the basics of ketones, what are ketones, what are carboxylic acids. We saw a little bit of IPAC nomenclature. And then we moved on to the nucleophilic addition reactions where we saw what is a nucleophile, right? And how do nucleophile come and it attaches to the carbon atom, right? So we saw addition of hydrogen cyanide, right? It was forming a cyanohydrin. So we saw what are the effects that we need to keep in mind. That is the steric effects, the inductive effect, right? And after that, we saw oxidation, that how an alcohol can be converted to carboxylic acid. Even ketones are converted to carboxylic acids. Aldehydes are getting converted to carboxylic acids. We saw certain reagents which are very good oxidizing agents like KMnO4, K2Cr2O7, and we also saw oxidation with the help of Tollens reagent and with the help of Fehling solution. Now, Tollens reagent is a very good oxidizing agent as well as it is used for a confirmatory test to confirm for aldehyde. Similarly, Fehling solution is also used as a confirmatory test to confirm for an aliphatic aldehyde. I really hope that you liked this topic, and if you want to study more in detail, as this was just an overview, if you want to dive deep into the topic and practice more of the board exam questions, so we can connect through Urban Pro and learn it in detail. Yes. So thank you so much for your time and attention.